I will do slides for this first topic. All right. It's the language that we use is slightly different from 547 classes, but it's very intimately related. We know from general digital control systems, 547 or any classes, undergrad, grad classes, we have these Z transforms, which connects the input-output signals in this fashion. We have the block diagram, and what it really means is in the Z domain, this is the signal relationship between the input U and the output Y. We write this Z domain relationship relates to the time domain, but we don't really want to write it this way because this is confusing. It is actually technically not very correct to write it this way because this is time domain and this is Z domain. So the two quantities are not in the same domain. You cannot you cannot multiply a signal in time domain with a signal with a Z domain quantity. So it is not correct. Sometimes if it's not confusing from the context, we will use it in this way. But the formal way to relate time domain signals is this technique called shift operators. So the shift operators are entirely in time domain, defined in time domain. We use Q to indicate it's a forward shift. So Q times UK is UK plus 1. And backward shift is Q inverse. Q inverse times UK is UK minus 1. We define it this way. So Q is the time domain shift operator, and it's perfectly fine to do Q times U. All right. This small change of notation is actually very important for adaptive controls. You can see the block diagram is very, very similar, and you will have no difficulty transitioning from a Z domain to this shift operator domain. But I would like to remind you, there are some differences here. Okay, let's do some common terminology first. Using shift operators is very easy to explain signal relationships. For example, moving average filter, where Y is UK minus 1 and add it together and then divide it by 2. So it's an average of the signal and it's moving, right? As K changes, Y will be an average of these changing two values added together. So that's a moving average, very common in digital signal processing. Another term that's very common it is called also a finite impulse response, or FIR filter, because if you do the impulse response of this filter, it is finite. It is not infinite impulse response. Another thing that's very common and useful to express using the shift operator is this one. You will hear very often people say autoregressive process. Autoregressive means this. Means the output YK, it autoregresses. So it depends on YK minus 1. It is actually an accumulation of the signal. So you can see the previous timestamp output is added to the input here, and the excitation is a noise signal. When you apply a noise signal to excite a filter that looks like this, you have an autoregressive process where you don't have numerator is 1 and denominator is a polynomial of the shift operator. This is called the autoregressive process. All right? So it is very easy to understand it. Now you see the shift operators. It is very easy to understand how this works as well. It is perfectly fine to write it this way based on the definition of the shift operators. And then you can do just algebraic operation for this transfer operator. So you can see this is yk minus q inverse yk equal to uk. So yk is yk minus 1 plus uk. This is the type of signal processing we do very often in adaptive controls. This is the autoregressive, where you have numerator is just 1. If your numerator is not 1, then you have a so-called, so this is autoregressive. If your numerator is not 1, for example, this one, then you have something so-called, it's a combination, right? It is a combination of this denominator components in the autoregressive process, as well as this numerator components, which occurs in our moving average filter on the first bullet point. So it's going to look like this. If you do the signal processing again, on this side, you have a moving average-like process, right? You have. Let's do it here. So the last bullet point is essentially this. You do on this side, we already talked about this is autoregressive. And on this side is a moving average-like process, right? You have UK plus UK minus 1. Okay? So this is moving average. Without the division by 2. So when moving average does not necessarily have to be normalized. If it's a combination of the previous signal values, it is still a moving average process. It is moving because changing k will change this value. All right? And this one is called infinite impulse response. In the more general sense, this is an infinite impulse response filter because it has poles, it has denominators. Okay? So from 547, you know that if a transfer function has denominators, it has poles. If you do an impulse response, it's actually going to have infinite lengths, all right, instead of finite lengths. Now, in the more general sense, we can write a signal relationship, input-output relationship in this way. We have an input UK, and there may be a noise, EK. Then there may be a transfer operator that defines the relationship between UK, YK, and EK and YK. This is perfectly analogous to Z domain, Z transfers, but in this case, it is expressed in the shift operators. And there is very strong reason to do it more formally, because if you think about, this is different from transfer functions. If you think about the definition of a transfer function, you will know that there are conditions for transfer function to exist, right? It has to be a linear, time, invariant system. But in reality, we already said the examples. Scenarios, vibrations, or practical disturbance, they may be time varying. And in that scenario, it is actually not correct to say the transfer function between this, in this time varying process, right? You cannot, it's not basically well defined in that sense. But shift operators won't be bothered by that, because it's just writing about signal relationships, all right? So GQ inverse will exist even if the parameters of the system models are time varying. And that is the difference between transfer operator and transfer functions. But when a transfer function exists, you can obtain the shift operator by replacing Z with Q, if a transfer function exists. In the literature, people have used also Q instead of Q inverse, just as a notation difference. But at the core, the core is really about the signal relationship, how the input will change the output, okay? The most common mechanical systems controlled by a digital controller can be written in this way. It has numerators, denominators, and usually we can pull out one backward shift operation in the numerator. So that means the plant has at least one step of delay intrinsically. And that is actually not difficult to understand. If we think about in practice how systems are controlled, normally we have the zero order hold. So and then the output. Suppose the scenario looks like this. I have a digital controller. I apply zero order hold to the signal, right? This would be U0, U1, and U2. This would be Y1. Y2, Y3. Without doing any math, you will recognize the fact here. When I look at my output at k equal to 2, when I look at this, you will see the input that matters, that was actually used to control my system. It depends only on, so look at this timeline again, right here. So it depends on everything in the past, right? It doesn't depend on here yet. I haven't applied this control here to my system yet. So because I'm using a zero order hold, you can see that at time k equal to 2, only the input up to time k equal to 1 actually matters. Right? So let's say there is an intrinsic shift of delay in the effect of my controls. Right? So it is exactly expressed in that transfer operator over there. If you take a look at that, you will see yk, let's say a pure delay operation. Let's say the example. What this really means, right? So here the example would be y2 equal to u1, y1 equal to u0. All right. In the most simple case, it is this kind of delay is happening. It's functioning in this way. My input u, my y will only depend on uk minus 1. All right? So this intrinsic delay operation happens. The intuition here occurs to the math in this way. So intrinsic delay is very common in practice, and sometimes we will just begin with this kind of models. Okay, We may sometimes use this to write as a system model. This is the most general possible transfer operator that we can use. But when we say we know we are controlling a digital plant, using digital controls, we are controlling a plant, sometimes we just begin by assuming the model of the plant will look like this. So this is applying as much as possible the prior knowledge about the system to do the modeling and identification of the system. And another thing that is also very trivial to understand is we will assume that the model, there are no common terms in the numerator, denominator. There are no common, there are no pole zero cancellations in these kind of definitions. So the model, we will assume that it is irreducible. We cannot reduce it to further. Question?
I have a quick notation question. Why do we call it B star?
Because you are one step ahead. Because I'm using the most general transfer operator in this here, and I use B. Okay? So here, let's put this into a little bit practice and then introduce a new concept. So in here, I already talked about this, and you can see actually BQ is having at least one step delay here. Okay? But in this slide, I'm using the more general transfer operator. So the general process here, it is defined in this difference equation. So YK depends on its previous values, and YK depends on the input UK. And then there is a noise term. And this way of modeling a system, there are many ways to model a system, in fact. And usually we apply as much as possible the engineering principles and concepts to understand the physics. All right. I will wrap up quickly by giving you some hints about how this is related. So basically, it's the same, just to apply the shift operator, YK. The difference equation basically means this, right? So when you have YK minus 1, it is nothing but Q inverse times YK. YK minus 2 is nothing but Q to the power of negative 2 times YK. Apply this to the difference equation, then you will be able to combine terms and obtain this term on the left of the difference equation. Then you can do division. This becomes AQ inverse. We'll talk about the details next time.